talk of the morning. We have Taiji Suzuki. Taiji is at the Tokyo University, and has has worked on many aspects in the intersection of statistics and machine learning, including density estimation and tensor factorization models. And more recently, has done nice work on deep learning theory. And today he's going to tell us more specifically about transformers and context learning. So thanks.
Okay, thank you very much. Okay. Good morning. So today I'm going to talk about some learning theory of transformers. Especially, I will talk about some in-context learning capability of the transformers. Okay. So transformer is used in many situations, like, of course, in the LLM, it is used, and also it is used in vision transformers. So it is very useful. And actually, it is very effective. Like, if you ask this kind of thing, like, please explain what is ChatGPT to ChatGPT, and ChatGPT response is like this. This is a much better than my response. So this is very good. So then we want to understand why does it work so well. So our approach is from theory. So in this talk, I don't talk much about applications, but I will talk more on the theories. Okay. So yeah, this is our motivation. And especially, so as I said, so we considered in-context learning. Okay. So I think that everybody here knows what is in-context learning. So this is a recap of the in-context learnings. Okay. So suppose that we ask this question to ChatGPT. Okay, please guess the number that fits in a question mark. Okay, so here is some examples. Here are some instructions. So for the 1, 1, the output is 2. For 2, 3, the output is 5. And for 8 and 13, the output is 21. So what is the answer against the input 5 and 27? The answer is 32. So the ChatGPT can answer correctly. So because this is a summation of these two pairs of the input. So maybe there could be some other rules that can satisfy this input and input-output relationships. But we choose the most natural relationship between the input-output, and then ChatGPT can do that. So it pick up one example, which is a summation over the two inputs. Then it can answer like this. Okay, so here's another examples. Okay, so left and right, dark and light, and up and what? So down. Okay. It is very accurate. Okay, so the very important point of the in-context learning is that the parameter is not updated during the instructions. This is very different from fine-tuning approach, like a human feedback reinforcement learnings. So if we present a new data point, so then the parameters should be updated by the gradient descent or back propagations. Okay, but for the in-context learnings, we fix the parameters. We just give some examples, instructions. So then it automatically finds a solution. Then it can answer the question. Okay, so that's an important part. So then our question is, why can we do that? Okay, okay. So to do so, we should present many tasks in a pre-training data. So we should present many tasks. Okay, so there are a bunch of tasks. In each task, there are a lot of examples, input and output pairs. Of course, as in real data, so we don't have this very much organized data. So these input-output pairs, so the input and answers pairs are embedded in some text. So, but anyway, so in the pre-training tasks, we present many bunch of the task, and then through this pre-trainings, the model will learn a kind of a distribution of a task. Okay, so they learn that there are some patterns of tasks, and then maybe so it can do a kind of task generalizations. Okay, so then it can do something like this. Okay, so to tackle this problem, so in this presentation, I want to present 3 works. The first one is a statistical analysis. This is something like a non-parametric analysis. And the second one is the optimizations. In optimization analysis, we consider so-called mean field limit regimes, in which we consider the infinite infinite width networks. So then we can analyze the dynamics. And the third one is a kind of mixture of these topics, the generalization and optimizations. And then so we can show a kind of one-step learning descent can do a feature learning for the in-context learnings. And then thanks to the feature learnings, we can reduce the sample complexity. So this is the plan of this talk. Okay, so now I'm going to the first topic, statistics. So this is a joint work with my student, Juno Kim, and my bachelor student, Nakamaki, and me. Yeah. Okay, so the problem settings that we consider in this presentation is like this. So in all situations, in all topics, so we consider this model as a data generation model, okay? So for each task T, so T is the index of a task. So for each task T, so we assume there is a true function FTO behind the data, okay? And for input XIT, so this is the ICE observation of the input for the T task. So there is a true, we operate a true function, and then here is an observation noise. So then YIT is the output for the input XIT. Okay, so for each task we have n pairs of XIT, YIT obeying this rule. So that is our training data. Okay, so so FTO can be different across the different tasks. So each task T, so we randomly generate FTO. So yeah, we assume some randomness on the true functions. Okay. So FTO is generated from some function class, so randomly. Yeah. And so in the pre-trainings, we have a T tasks. So each task has n data points. Each data point is input out pairs XIT and YIT. So the model observes n data point in each task. And so the number of task is the T. So after pre-training on this data set, so the model will observe some test instructions. Okay, so XIT, YIT. So it again observes the input data for the new task. But here, we don't assume that the model we don't assume the model updates their parameters. The parameter is freeze after the pre-training. So then we make the transformer model perform the in-context learning here. Okay, so then we expect that the model can answer the correct output Y query for the new query, input X query. Okay, so this is a kind of a base estimations. Okay, so in the pre-training, so that the model learns something like a distribution of the problems. So that can be a kind of prior distribution. So it learns it estimates the prior distribution of the problem, and then based on the prior distributions, it is expected that the model will perform a kind of posterior inference at this test phase. So then our theoretical question is that how the transformer can reach the almost base optimal estimation errors. Okay. Okay, so as for the true function FTO, so this is what we want to estimate from the data. We assume this very simple linear model. So of course, we can consider a kind of a composite function like in a chain of thought. But yeah, we consider the simple settings, okay? So here, FO, so small FO, so this is infinite many features, okay? So for input X, so FOX has an output of infinite dimensional vectors. So this is a kind of a nonlinear features. The nonlinear feature dimension is infinite. And the true function FTO can be written by a linear combination of those nonlinear features. In other words, so we take an inner product between beta t and the infinite dimensional vectors. So here, beta t is a random variable, which is independently generated for each task t, and that has a mean 0 and variance sigma. So, this nonlinear features FO is shared across all tasks. So this is common all tasks. But the only beta t, the coefficient, varies across a task. Okay. So here are some examples. So if you choose a B-spline basis for the nonlinear features of FO, so then the true function FTO could be like a member of Bessel space. So Bessel space is a kind of generalized version of a Sobolev space with some smoothness alpha. Okay, so if you choose a Fourier basis as a basis function of this function, so then we have a Sobolev space. But anyway, so we can choose any nonlinear features as a basis functions. Okay, so what we expect the model should do for this task is something like this. In a pre-training stage, so that the model we should learn the feature map FO. So this is shared across the task. So then the model should learn the nonlinear features. Okay. And so then we expect that the model will learn the most compact representation of the nonlinear features. So otherwise, if there are some redundancy, then it will affect the generalization errors. So the model should find a kind of the most efficient representation of the basis functions. Okay. And moreover, in the test phase, so the model should estimate the parameter beta t. Okay. So because this is not common for all the tasks. So beta t is specific to each task. So for each task, beta t should be estimated depending on the instructions. This can be done by attentions. Okay, so by looking at the relationship between the input sequences, so then maybe the attention layer can find the coefficient beta t. Okay. And this observation is a little bit motivated by this work. Guo and from Oswald et al. So they observed a very some interesting fact that real transformers in practice extract nonlinear features in the lower layers, and on the deeper layers they perform a kind of regressions. Okay, first they perform a nonlinear feature extraction. On top of that, the transformer do a kind of linear regression to find the beta t. Okay, so in the lower layers, so they find a kind of nonlinear features, and on top of that, they find the coefficient beta t by performing a kind of regressions. Okay. So to perform this one, so we consider a very simple transformer model. Okay. For each token x, we apply a neural network, fully connected neural network phi. So phi takes an input, d-dimensional input. So each token comes to this neural network as an input. The output is the n-dimensional features. So because a neural network cannot have an infinite dimensional output, so we should consider like a finite dimensional output. So the dimensionality of the nonlinear feature is denoted by n. So in other words, we truncate the infinite dimensional features at n dimensions. Okay, so this is a true features of the true functions. So we truncate it at n. So index n. So yeah, so we want to approximate about the FO by the numerator phi. Okay, so after we extracted some nonlinear features by neural network, we applied some attention operations. Okay, so we consider a little structured attention. So this is not a very exactly the same as the real attentions, but anyway, the intuition is very easy to understand here. So phi xi is the nonlinear feature for the input token xi, and then we calculate the similarity between this key value and the query value. So query is the nonlinear feature for the query input. And so here's a KQ matrix. So we consider a kind of a metric defined by the KQ matrix, and then we calculate some similarity between xi and x query through this inner product. And then, so depending on the similarities, we take the weighted sum of the output yit. So this is the value. So this is the output for the ice tokens, xi. So by doing so, we can perform a kind of a nearest neighbor things. Then maybe we can perform something like a non-parametric regressions. Okay, but here, so we consider a little bit more simpler situations where we consider linear attention models. So this is a bit very strong, very large simplifications but yeah, so many several chains have been doing something like this. So, but we follow that simplifications. But anyway, so we drop this exponential term and we consider only the linear interactions between key and queries. Okay, so yeah, the intuition is the same. So we calculated similarity between xi and s query, and depending on the similarity, we define a weight, and then take the weighted sum of the output by t. Okay.
So in a standard setup, you would have like the x and then the y and then the x and then the y.
Yes.
Here, you're just going to stack them.
Yeah.
Right. So you don't have to worry about like moving the information over. You just have, because we know networks can copy stuff over one token. You're going to throw that away.
Yeah.
And then you are approximating all of the early layers, you know, sort of like a pure NLP model up to this attention layer as like one big nonlinear extractor.
Yeah, that's right.
Sort of like this model is like sort of like a transformer, except like you fix a previous token head and then you do pure NLP and one attention head.
Yeah.
And that would be D1.
Yeah.
And then you're going to say, furthermore, no denominator, linear attention.
Right. Yes, exactly. Right. So of course, in practice, there are a lot of layers between them, but so we omit all of them. And then so maybe in practice, we start from attentions. And then after that, there is a nonlinear feature, but we simplify that like this. So that first, just nonlinear feature extraction and attentions. And then so, yes, so we omitted this one. So.
Right. In particular, we will not let the model sort of do interesting nonlinear things, combining phi of x1 and y. Right. So you can't use the value of y and mix it up with
No. So yeah, so that's another simplification. So it must be like, so phi must be phi and phi y. So there can be like a, so no, phi x, y should become here. But yeah, this is much more like simplification. But in terms of the explicitability, so yeah, so we can put the y here, but it is much more representative. So it doesn't hurt the theorem in the following. Yeah. Okay. So yeah. So we consider this linear attention model. So from now on, so we write gamma. We use the notation gamma to represent the K2 matrix. Okay. So here we use this one. Okay. So the interesting point of the linear attention is that it can perform a ridge regression. So this is pointed out to many authors like this. Okay, so the ridge regression with the regularization lambda is also formally written by like this. So then it can be expanded like this. So yeah, so yi phi xi transpose and the inverse of the design matrix, and then phi x query is coming here. So if we replace this term by a gamma, so maybe so gamma approximate this inverse matrix. So then this formulation is same as the linear attentions. So linear attention can approximate the ridge regression here. Okay. So if we choose gamma, so this matrix very carefully, so we can achieve a kind of Bayes optimal estimation. So because if you choose the regularization in ridge regression very correctly, so that it can perform a Bayes optimal estimations. So yeah, in that sense, the linear attention can do a kind of Bayes optimal estimation if we know the nonlinear map phi. Okay. So this part works as an estimator of beta t. So for each task t, so we calculate this one, and this becomes a kind of a estimator of the coefficient beta. Okay. So so we need to find a gamma, and also so we should find a good representation, nonlinear representation phi. So it can be found by minimizing this empirical risk. This is so we just consider empirical risk minimizer. Then the question is how small the expected risk can be through this empirical risk minimization. Okay. So here is the result. So this is we are following the very classic non-parametric regression analysis, but it is extended to in-context learning settings. Okay, so we put some assumption like this. Okay, so remember that. So the true function is given by beta t transpose fo. So we assume that the coefficient beta t decrease in some sense. So this is the first assumptions. So beta tj square is basically bounded by j to the minus 2s minus 1. So the S represents how fast the coefficient decays. So if the coefficient does not decay, so then it is very difficult to estimate. Okay, so because we need to take care of many basis functions. But if S is large, so then the beta Tj decays very rapidly. So we don't need to take care of infinite many features. So we can truncate at some point. So then the problem becomes much easier. So then the S controls the complexity of the model, the problem. Okay. So this is the first example, assumptions. And the second assumption is that so each basis Fj O can be approximated by neural network with the precision, the accuracy delta n. So this is our assumptions based on some function approximation theories. So usually like a cosine and a sine Fourier basis can be approximated by neural network very efficiently. So yeah, this is very natural to assume. Okay. So under these technical conditions, so we have this upper bound of the test loss. Okay, so it is very complicated, but we just needed to take care of these three terms. Okay, the first term, so this is the approximation error for the features. So because we are truncating the infinite many features at dimension n, so there must be some residual. That residual can be upper bounded by n to the minus 2s. So if the beta t decreases so rapidly, so then it's okay to truncate up to the n dimensions. So then the S affects the ratable components of this approximation error. Okay, and the second one, so this term is the complexity to estimate beta t. So we are, yeah, as I said, the attention is doing a kind of a rigid regression on the n-dimensional features. So then the complexity becomes like n over small n. Small n is the length of the sequence. Okay, so then the third one is the complexity to estimate basis functions, because before the pre-training, we don't know what basis function is appropriate to represent the target function. So we should estimate it from the data. So that complexity is coming here. So yeah, this is a log covering number of the neural network to approximate the basis function. But anyway, so this is a kind of BC dimension of the neural network. Okay. So log covering number times 1 over t is coming here. So if you have a lot of pre-training tasks, so then this term becomes small. But this is a very complicated, so I would like to show concrete result for some examples. Yep.
Gamma is like if you were to just fix gamma at identity.
No.
Have it be subsumed by these. How would that change this?
You mean, so what happens if we fix the gamma to the identity? You know?
Right, and so then that linear component gets subsumed by the DNN that corresponds to P.
Okay, well, so gamma must be, okay, so, so gamma is also, so gamma contains some information about the variance of the covariance matrix beta t. So, but by choosing the phi appropriately, so then we can whiten the beta t. I mean, so the correlation between the beta tj and the beta t, so the coordinate of beta t can be vanished. So then by changing the coordinate, so then so gamma equal identity also works. Yeah. So I mean, we can yes, so we can reduce the freedom of gamma to the freedom of phi. So yeah, so you're right. So we can choose gamma to be the kind of identity. Yeah, that's right. But we need to take care of the scale of the phi j. So each element of the output phi should be correctly chosen. So otherwise, we don't have a right scaling to obtain this the upper bound. So yeah. Okay. So okay, so here is the concrete examples of the upper bound of the expected risk. Yes, so suppose that each basis fj is a B-spline basis, then the true function is included in so-called the Bessel space or Sobolev space. Then we have this ratable convergence. So this part, the first part is well-known minimax optimal rate to estimate beta t. Okay, so if we know the basis function phi fo beforehand, so then this is the optimal rate. The second term, so this is the cost to estimate basis functions, because we don't know the appropriate choice of the basis fo. So we should pay this complexity to find a good basis that represents the data very well. Okay. So if the t is large, so the second term is negligible. So then we only have this first term. So this is an optimal rate, so that any other method cannot go beyond this rate of commodities. Okay. So, but if the t is small, so then we cannot find a good representation. So then maybe the model lacks some information to represent the new task. So then we don't have a good generalization. So in other words, in small t regimes, so that we don't, so in the pre-training, we don't see a lot of pre-training tasks. So then it's a kind of memorization schemes regime. So we are still memorizing, the model is still memorizing the task. But if you have a lot of tasks in a pre-training, so then it starts the generalizations. Okay, so the same thing also happens for the more complicated situation where each basis is included in a Hilda class with smoothness alpha prime. So the same, but this term becomes a little bit larger, but the same thing happens. Yeah. Okay, so we also have a kind of minimax rate for the in-context learning. So the minimax rate becomes like this. So here the minimax rate is the optimal rate of for all estimators. So not only the in-context learning, but also fine-tuning method is included in this the class of estimators. Then the lower bound becomes like this. The first term is the same as the upper bound, but the second term is a little bit different. But anyway, so if t is 1, so if there's no pre-training, like so very small number of pre-training, so then we needed to learn the input-output relationship from scratch. So in that sense, situations, the estimation error, so the expected risk can be bounded by this quantity. So then if the basis function is very hard to estimate, I mean, the basis function is included in some Hilda space and whose smoothness is not so like smooth. If the basis is very difficult to estimate, so then this term becomes dominant. So this is a sample complexity to estimate a basis function. But if the t is large, like if you have a lot of pre-training tasks, so then you can estimate a basis function beforehand. And then in the test settings, you just need to estimate the coefficient itself. So then the rate of convergence becomes much better. So, yep.
So there's three numbers. There's the number of tasks.
Yeah.
There's the number of pre-training examples.
Yeah.
That include repetition per task.
Yeah.
And there's the length of the context.
Yeah.
What
length of
the variables?
Length of the context is the same as the number of data points in each task. So that is denoted by n. N is the length of the context. You are given n examples for each task, then another x-ray is coming.
I see. So in this t equals 1 case, pre-training consists in that case of one autoregressive sequence.
Right.
And then testing would be another autoregressive sequence.
Yes.
Like, I'm confused that you could win at all there. It seems like, you draw, so you're running with one function and you learn that based on that, to get really high accuracy. Like, how do you even get a?
Okay, so maybe this was confusing. So what we consider is a t equal like 0. So t equal 1 is just just the number of tasks in the pre-training is very, very small. So we cannot get any information in the pre-training.
Right. Sorry.
So
this is the lower bound. And so if we go to the upper bound slide.
Okay.
Before, so the upper bound slide, when t equals, if t were 1, then n is, then the numerator is larger than 1, right? And so this is backwards. So
yeah, it's a backwards.
If you're doing this in a pre-training ICL way and t is 1, you get nothing.
No, nothing.
But you're saying that no matter how smart you are, for example, you could be doing active learning,
Yeah.
Right, would be an estimation scheme. If you're doing active learning, right,
Mm.
then of course you don't need pre-training. You would be doing it on that task, and then you get a lower bound.
Oh, that's right. You're right. Yes. So of course, in the ICLs, we don't update the parameter in a test phase. So if the t equal 1, it's progress. So we don't have any. Yeah, but here you can update the parameters.
Any learning scheme you want.
Yes, anything is allowed. But still, we see the separation between many tasks, many pre-training regime and a small, many pre-training tasks and a small pre-training task regimes. Yeah, so that means the pre-training helps actually. Okay. So this theoretical result also coincides with some experimental results. So these guys did this experiment. So basically this is the optimal ridge regression. This is the base optimal errors, and this is a transformer trained on the pre-training. So as the number of pre-training tasks increases, so then the expected risk will converge to the optimal errors. So this coincides with our results. So actually, if you look at this upper bound, this upper bound, if t is above some threshold, so the second term is negligible, so the first term is dominant. So this is the optimum rate. So when we know the basis functions, so then it coincides with the optimal ridge regressions. Okay. So then now I would like to go to the optimization sections. Okay, this is also a joint work with my student Juno Kim. Okay, so the problem setting is the same. Okay, so this is just a recap of the problem settings. We consider this non-parametric regression problem. Yes. Yeah. So, to show the global optimality of the gradient descent, we consider a little bit simplified settings where the true features is not infinite dimensional. It is a k-dimensional. Okay, so f of x is a k-dimensional. So behind the data, so there is a k-dimensional nonlinear features, and then so the coefficient of vt is generated from some Gaussian distribution. So vt can depend on some task, each task. Okay, so then we want to estimate vt from our linear attentions, and we should estimate fo as well. So to estimate this basis function fo, so we use so-called mean field neural networks. So basically, this is a two-layer network with very wide width. So what is the mean field network? And so it can be written by this formula. So h theta is the one neuron. So h theta is one neuron with the parameter theta. So where sigma is a nonlinear activation, so w is a first phase parameter, and a is a k-dimensional vectors. So we take the average, so we take some expectation of h theta with respect to the parameter theta. So we assume there is some distribution mu on the parameter space theta, then we take the average over the parameter theta. Okay, so this is called a mean field neural network. So by using this two-layer network, we extract some k-dimensional features, and we feed such a k-dimensional features to the linear attention. Then we can perform a kind of ridge regression on top of this finite dimensional nonlinear features. Okay. So why we need to consider mean field neural network? Okay. So it can be considered to be an infinite width limit of this this mean field neural network. Okay? So each neuron has a parameter. So suppose that each neuron has a parameter theta m, and then we take the average over the m neurons. So now we take the infinite width limit. So then maybe this summation could converge to the expectation over the parameter theta. So this is called the mean field limit. Okay. The benefit of this representation is that, so if you look at the parameter itself theta m, so this is a highly nonlinear model. So this is not linear with respect to the parameter theta m. But if you look at the distribution of the parameter, so if you look at, if you lift up the problem from the parameter to the distribution of the parameters, then you have a linear model. This is our kind of infinite dimensional linear model where the parameter is the probability distribution of the parameter theta. Okay. Okay, so this is a linear with respect to the distribution mu, and this is non-linear with respect to the parameter theta. So then even if the loss function is convex, so this is the loss function is highly non-convex with respect to the parameter theta m. But it could be like convex or nearly convex with respect to the distribution mu. So this is why we employ this formulations. Okay. So actually, to optimize the two-layer neural networks by applying so-called mean field arrangements, we can have an exponential convergence like this. But this is not what I want to talk this in this presentation. So, yep.
Just instead of thinking I've got 100 neurons and I'm going to vary the parameters of one of the neurons and see how the output changes. That's hard. You're like, I have all neurons in the universe, and I'm going to vary how much of each member of that family I have. And that's like a much better behaved.
So could you say again? Yeah.
So just like you're here, like this is a sort of infinite neural network where like every kind of possible weight for every neuron like is present, and you're just saying I want more of this as opposed to like varying, like losing one neuron when you like add another.
You mean so? You mean so? Even though we drop one neuron, so then the network is not changed.
Yeah, maybe I was just trying to get some intuition, but maybe I should.
Yeah, another way to ask the question is if having an infinite distribution where you're including all directions and having a weighting over all of them is simpler than having a finite discrete. Yes.
Because I guess a classic neural network is delta functions. Mu consists of some set of delta functions.
Yep.
And the changes you make is you slide one of the delta functions. And here, which is like a really big change, because you're like all of this guy and adding all of this in. We're just making moderate changes.
You're right. You're right. So instead of changing the location or the parameter theta m, but we change the weight of the parameters. So and then changing the location of the delta function gives you a landscape where the one on the left, whereas changing the weight is giving you a landscape. Then that makes a convex program. So if you change the location, it is a non-convex program. But changing the weight is like a convex program. So that's our intuition. But in the implementations, we also update the theta m. So So like to update the distribution mu, so we usually consider so-called Wasserstein granite flow. So then, we also change the location itself. That's a difficult point, but So anyway, so even in that setting, so we can show the convergence. So that's a theoretical difficult part. But the intuition is like that. Yes. Okay. We have another 5 minutes. Okay. So this is our model. So what we want. So then next, as in the previous slides, we want to minimize the empirical risk with respect to the distribution parameter mu and the transform parameter gamma. Okay. So this is a highly non-convex. So it's very difficult to optimize. We want to show the global optimality or something like a granny descent. So, but to analyze the empirical risk is a bit difficult. So we consider a kind of a simplification like this. We take the sample size equal to infinity, and then we consider the expected risk instead. So we analyze this one for the optimization guarantee. Okay. So but it's difficult because there is a quadratic, some kind of a second order relationship between h mu and h mu, and here it's also gamma. So this also should be optimized. So this is a third order interaction between the parameters. So it's a bit difficult to optimize. Okay. So but the one good point is that the objective is linear with respect to the parameter gamma. So this is the parameter of the attentions. In other words, it is a KQ matrix. The KQ matrix here is linear. So its optimization is easy. So then we first, for each iteration, for each fixed mu, we optimize the gamma first. In other words, we consider 2 time scale optimizations. we optimize gamma first, and then we update the parameter mu. So mu is updated, so the gamma is optimized, and the mu. Then after that, we update the mu, and the gamma is optimized. So yeah, so let us consider that such a 2-time scale optimization procedures. So then this objective function becomes a function of the distribution mu. Okay. So here sigma mu is defined by some correlation between h mu and h nu. But anyway, so there are very complicated that correlation appears. So like a fourth order correlation appears. So then the objective function is very far away from the convex objective. So we want to optimize this with respect to the distribution mu. To optimize this objective, so we use so-called Wasserstein gradient flow. So this is a very usual way of optimizing the distributions. But so if you look at if you use a so-called particular formulation of the Wasserstein gradient flow, so it becomes like this. So suppose that we have infinitely many particles to represent the distribution mu. So each particle is updated by like gradient descent like this. So this notation is a bit weird, but this is basically the gradient descent. So okay, so this is a change anyway. So we do some gradient descent for each particle. So then the distribution is updated. The dynamics of the distribution can be written by this continuity equation. So then does it converge to global optimal or not? So the one good news is like this, even though the objective looks very, very complicated like this, but it has a very simple structures. It is a strictly subtle. So what is strictly subtle? So even though objective is very complicated, but there is no 3S local minima. Okay? And so every critical point is a saddle point or a global optimal solution. So every saddle point has a negative curvature with lower bound. So its curvature is lower bounded by some constant. Okay, so then if the solution is a little bit away from the saddle point, it can escape from a saddle point in exponential orders. Then it will converge to the global optimal solution. Okay, so yeah, and so this is very much analogous to matrix completion analysis, which has been developed in like 8 years ago. Yeah. So this is the more mathematically correct descriptions. Okay, so yeah, and some assumptions like this. So the density ratio between the two target distribution and our solution is bounded. So then we have the convergence of the Wasserstein gradient flow to the global optimal solution. Okay. So I don't have the time to the final topics, but okay. So I gave just a brief introduction. Okay, maybe Danny has already talked about this one, but okay, yeah, somewhere. So I want to give some intuition here. Okay, so the problem setting is almost the same as the previous. Okay. So I should skip this one. Okay, the problem setting is the same, and so yeah, so just one sec gradient descent, so we can find some low dimensional subspace, and then yeah, we can do a kind of dimension reduction. So, but yeah, I wrap up the presentations. Okay, so yeah, so in this talk, so I have considered to estimate this kind of function in context settings, and then non-parametric regression. So there appears some trade-off the number of tasks and the number of the data points. So if you have a sufficient task diversity, so we have a minimax rate. Okay, so yeah, so and in optimizations, we have shown that the mean field neural network can achieve the global optimal solutions, and the objective becomes like strictly subtle. And what I skipped here is that, so if the true is a single index model, then just one gradient descent can find a direction, so in which the single index model is informative. Sorry, I skipped this one. Yeah, so yeah, that's it. Thank you very much.
Question for time for question maybe on that.
So very, very interesting talk. One thing that papers on linear attention have noted with regard to the squares is that matrix gamma, it's rooted to the distribution of the x's. So if a novel task presents that has a different X distribution.
Okay. Yeah.
So,
Okay. We don't assume that. We assume that data distribution, X distribution is the same. So otherwise, we don't have a base optimality. So that's a very strong conditions. But in practice, the X distribution will be different, and that can has information. Oh, X is different. So maybe this is some specific this task. So that could be help to have a much better generalizations. But we haven't considered that situation. Yeah.
Okay, that's thank you again.
Thank you very much.
Sorry a second. Sunny, yeah. When were we back? Sunny? When are we back? 2:15. It's good. Okay, we're back to 2:15.
If anybody for lunch, the back place is really close, good food, and it's low cost, and it's a really nice building.